going on, everybody? It's Mr. Gustin. I'm back in the physics classroom. Today, we are working on continuing our study of torque and equilibrium. Particularly, we're working on our use of FR sine theta. Last time we talked about what this equation actually means, and right now it's not an equation. Right now it's just three variables multiplied together. But essentially, we talked about what each of these variables means in the torque expression. We talked about force being a push or pull, R being a measurement or a distance measurement between an axis of rotation or a pivot point and the location the force is being applied. R needs two reference points. It's the pivot and the force. It's that measurement there in meters. And then lastly, sine theta, that angle is the angle between the force and the radius. If this thing is perpendicular, then sine theta is 1. And if force and radius are parallel, then there is no torque being produced from that force. And so this torque would be 0. Today, we're doing design a Sine Lab. Here's essentially our setup. I've got hook sticks again. Our challenge is to find the mass of this hook stick using a sine type setup. And I mean sine, S-I-G-N, not S-I-N-E. So here's what I have. I've got a monkey bar set up here with the right angle clamp. And I'm using the right angle clamp as kind of a tuner. I got a string, maybe you can see this, a string wrapped around this screw on the right angle clamp, and I am going to hang this from my, there we go. Why is this not working? This one, whatever group used this setup may have not done a very good job. I don't know how they did it. I don't know how they pulled it off. Maybe we'll try this way. Is that going to work? That's not going to work. We're moving to a new sign. I don't know how this group did it. Let's go over here. Same setup here. I'm going to hang my hook stick from my right angle clamp in the right way. And there we go. It's on there. And now I'm also going to attach my spring scale to my hook stick. And so here's essentially my setup, and it kind of looks like a sign, right? Like an awning where you'd see here's a beam and a tension cable that would hold. We may even add something down here, like a sign you'd see out on the street or whatever. And there are two setups to this, okay? The first, part one, is we're going to use gravity perpendicular, or a perpendicular component of gravity to determine what this, let's get this thing right here. I want to figure out the mass of this stick. And so the first thing I'm going to do is I'm actually going to level my hook stick, my torque board, okay? Once it's level, that means a couple of things for my picture, right? If it's level, then I know FG is pulling straight downward as opposed to FG pulling at an angle. So let's draw a picture. We have two parts to this problem. Here's part one, and part two will be over here. Part one, I've got my hook stick. There's my hook stick. It's pinned right here. It's fixed right there. There is a string pulling up right here with my force sensor right there, and then here's my beam, okay? So when I think about this picture, there are a couple things I need to consider. There's clearly a tension force that I'm getting measured there. There's clearly a weight force right here. And what's actually pretty neat is that I can see both of these forces. And I'll show you in a second. I can actually see the hinge force in the x direction and the hinge force in the y direction. If I come over here and look real closely, what I can see is the hook touching the pin. I can see my pivot point. Basically, if I were to snip this string, this whole system would fall down and rotate around this point. And because of where this hook is sitting, I see that the hook is on top of the screw. So the screw is applying a normal force upward. That's my hinge in the y direction. And I also see that the screw is touching the hook right here, which means the screw is pushing this way in the x direction. So I can see my hinge forces when they are in contact. So that's pretty neat. So my FBD looks like that. Let's take some measurements and fill some things out. first things first, every hook is 10 centimeters apart, and this first hook is my axis of rotation. So if I count to find where is the tension force being applied, tension force is being applied at a distance of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is 10 groups of 10 centimeters away from the axis of rotation, so that means it's a meter away. So let's go add this to the picture. The length here is, from there to there, is 1.0 meters. We can go find where the middle of the board is. The middle of the board is at my middle hook, and the middle hook is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right here. And so how far away is that from my pivot? It's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It is half a meter away. I wanted to double check that. So from the pivot to here, this distance here is 0.5 meters. And then my tension force comes off of the spring scale, so let's get that reading as well. This reading over here says it is 5.2 newtons. So the tension force required to support this stick is 5.2 newtons. Okay, this is my picture. Let's go ahead and look at the net torque expression. There are only two forces producing torque here. So my net torque, this is stationary. This is equal to 0 Newton meters, and I see a torque from weight, and I see a torque from tension. So 0 Newton meters is equal to mg. We're not using FG anymore. It's February. Stop using FG. It's mg from here on out. But that's force of gravity, F, times R, which is R to the middle of the board. We'll call it RG, just so we know it's R to the gravity, or to the center of mass, times sine theta. Again, that angle, sine theta, angle between force of gravity and R. Here's my R, 0.5. Here's my force of gravity. That is a right angle. Is there an angle? Yes, it's 90 degrees. Sine of 90 is 1. I don't need this here. I can call it sine 90 if I want, or I make it a 1 and I get rid of it. I prefer to get rid of it. There's no component. All of gravity is causing torque. Minus Ft, which is straight up off of here. I'm not going to replace Ft with some variable. Ft is recorded. I measured it using a spring scale. Times R to the tension force times sine theta. Is there an angle between the tension force and the board? Here's my radius or my distance measurement. There's the tension force. You betcha there is an angle. That angle is 23 degrees. So as I go plugging things in, m, that's what I'm solving for. 9.8 meters per second squared times the distance, that's 0.5 meters, minus Ft, I recorded that, which was 5.2 newtons, times R, which is 1 meter, times sine of 23 degrees. Folks, you go figure it out. What is the mass of this board? It should be anywhere between 350 and 500 0.35 and 0.5 kilograms, or 350 grams to 500 grams. It's somewhere in there. That's part one. Part two, to verify our answer, we move this in a little bit of a different way. Instead of having our board be level and balanced, we crank it up and we make it much higher. We actually make our string level as opposed to the board being level. This causes a little bit of a change in what we're seeing here. All right, I try to get my string to be as level as possible, and that looks pretty level. I want this hook and this to be as close to the same height as possible, and that looks like what I have right here. Okay? So this is my new setup. I'm trying to get this as flat as possible, and when I finally get that as flat as possible, I have a new picture. So let's go ahead and sketch that out. Picture time. I've got my wall. Here is my beam. Here's my axis of rotation, and then this is my tension force. At this hook, and I've got my spring scale loaded up right here. Bang, 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 bang. Clearly a tension force, clearly a weight force. And then if we look to see where our hinge forces are, we can look real closely. Where are these things touching? Well, in the Y direction, we see it's touching on top, so the pin is pushing up. And in the X direction, we see it's touching on this side, so clearly it's pushing that way. So our hinge forces look similar to before. I've got a F hinge Y, and here is a F hinge X. These are my 4 forces. We're going to need some measurements. So let's get them. I'm going to grab my phone so I can get my measure app out. And I can get my angles as well, okay? So first things first, let's take some measurements here on distances. The distance from my pivot to the center of mass, that hasn't changed. It's still 0.5 meter. Distance from the pivot to the tension still hasn't changed. That's still 1 meter. This force, though, up here, this force is now 4.9 newtons. So I'm going to go record that up here. And the angle that we create up top, which is an interior parallel angle to this angle down here. Let's zero this thing out. Let's figure out what my angle is down here. My angle says it's 24 degrees. So we're going to use 24 degrees as my angle at the top. That's this angle right here. Why is that angle so important? Well, that angle is so important because I want to know the angle between the radius or distance to Ft and the Ft force. Let's go ahead and write our net torque expression. Equals 0. I've got torque from Fg minus torque from Ft. Torque from Fg, 0 Newton meters. This is mg times r to g times sine of theta. We'll call it theta 1. Where is theta 1? Theta 1 is the angle between the weight force and its lever arm. How far is Fg away? Here's the pivot. There's Fg. You see that distance. You can see this imaginary line right there. There it is. Where is Fg? Fg is right here. Well, that angle then must be right here. That's theta 1. Is that the 24-degree angle we just measured? It is not. That's up here. This is a different angle. We actually measured this angle here. If that's 24, 90 minus 24, 66. 66 degrees is going to be this angle. Minus Ft, which we measured 4.9, times the distance. Let's find that distance. There's the distance right there. Here's my r. There's my Ft. The angle between those, we'll call that theta 2 times sine of theta 2. They are different angles. They are different measurements. Theta is not just a number we pull out of thin air. It means something. It references our equation. It's force times distance times sine theta, and that theta is the angle between those previous 2 measurements. Folks, I'm not solving this for you. It is in your packet. You have the data. Now that we've got the picture and we've put the appropriate variables into the equation, you should be able to do this. If you can't, send me a comment below. Send me an email. Ask me in class. Until next time, see ya!